Jay, you and I have been talking about NVMe over fabrics for a while. I know it's been a big part of your world. I know that you've given this presentation in some flavor or another in multiple forums, because if you do a Google search, your name comes up attached to this content quite a lot. Now, this first came to my attention just because NVMe and the bus speed gives it the ability to fill 100 gig pipes. And that made me think, gosh, there's got to be some impact to network design, especially for converged fabrics and so on. And then very recently, NVMe over TCP was standardized. That happened last month, I believe. So
yeah, 4 weeks ago.
Jay, you're an authority here. I'll let you go to it.
Yeah, so you can hear me okay, I hope, yeah?
Yes, sir.
Awesome. Awesome. Yeah, well, thanks for inviting me to talk a bit about this, because you're absolutely right. There's been a lot of questions in the last 6-7 months or so in particular, because the NVMe over fabrics is starting to bleed into the normal networking nomenclature. So quick introduction, my name is Jay Metz, and as Ethan has mentioned, I do an awful lot of writing, presenting, talking, about storage, but lately it's been primarily NVMe all the time. So they asked me to come and talk a little bit about how Ethernet network design for NVMe over fabrics can really affect it. I've been here all day. I've been listening to all the different sessions, and I got to tell you, I've just been feeling hopelessly outclassed by a lot of the networking people here. So I feel like you have invited the heretic into the mix.
So, yeah, we're going to burn you at the end. Don't worry about that.
I have no doubt that there's already effigies with my face on it, or at least a hat. So we'll have to see. But we do have a lot to go over today, so and not a lot of time to do it. So I'm going to go by my way of introducing myself by saying that I am a member of the board of directors for not only NVM Express, but also SNIA and the Fiber Channel Industry Association. And so I'm someone who looks at this kind of technology from many different angles, and I hope that I can package it up and present it to you in kind of a holistic fashion. And so despite all that, and despite the fact that I work for Cisco, this is going to be a vendor neutral kind of a thing. I'm wearing a vendor neutral hat. I'm wearing a kind of a no proprietary technology motif. So this is all stuff that's standards based. So right now, as I said, there's a lot of interest in the relatively new kind of storage called NVMe, non-volatile memory express. Now, of course, anybody who's been paying any kind of attention knows that it's extremely high performance. And obviously that means that people are curious as to what's going to happen when that kind of traffic gets put over a network, hence the reason why we're talking about this today. Now, it's important to note that NVMe comes from a world that didn't originally take networks into account. So many of the concepts may be foreign to the average network engineer. However, because of the fact that most people here are more familiar with networking than with storage, we need to build a bridge between the two. So we're going to be level setting with a bit of an NVMe and NVMe over fabrics primer, often shortened to just fabrics. We'll also be talking a little bit about what makes a storage network good, and we'll be discussing some of the different approaches to how storage and networking intersect. One of the things that we will be talking about over and over again is that not all storage networks are equal, even if they all happen to be using Ethernet. So to that end, we will be discussing Rocky, iWARP, and TCP-based fabrics, while keeping one foot in storage and the other in networks. Now, finally, we're going to be bringing everything together by circling back to what constitutes good storage networking philosophy as it applies to NVMe over fabrics. All right, so we're going to start our headlong dive into the specifics, and for some this may be rudimentary, and for others it may be completely new. So hopefully we'll get the level setting done properly. One of the things that'll be useful to keep in mind, and I'm going to be repeating this consistently throughout the presentation, is that NVMe treats storage like memory. That is, for decades we saw storage, especially network storage, as simply a device on the other end of a wire. And because we saw it as a device, it was easy to think of it as separate and isolated from not only the host, but the network as well. NVMe, on the other hand, sees storage through the lens of memory semantics. And if you keep that in mind, along with all that entails, then the logic behind the networking requirements will start to make more sense as well. So NVMe works on the basis of queue pairs. There is an admin queue, which is used for controller management, which is the controller management is what is on the storage target side, and I/O queues, which are used for I/O. So these queues can be really deep, up to 64,000 queues and up to 64,000 commands per queue. In reality, you're not going to see nearly that many queues put into practice because they're still memory bound, and it will take a lot of memory to be able to handle that many queues and that many commands. So you're not going to see anywhere near that amount, but the capacity and the capability is there. So these queues are the connections between the host and the corresponding NVMe controllers on the storage side. And as you can see by the image, you can have multiple submission queues per completion queue and multiple queue pairs per CPU, each pinned to a specific core. Now, this association between a host and a controller within a subsystem is called the multi-queue interface model. And it's really kind of the magic behind what makes NVMe so high performant. These queue pairs are the key to understanding how NVMe works at a high level. Unlike in SCSI, which requires all of the I/O to go through an adapter in order to communicate between the host and storage, NVMe allows each of the queues to submit and complete independently from one another. So that way you don't have to have locks between the CPUs or the CPU cores depending upon the I/O, and you can actually do source core interrupt steering. And that is where the core submits that submits the request is the same core that receives the completion back and interrupt when it's done, so that you don't interfere with other I/O facilities and other cores. That is a very key element as to why NVMe is what it is and why it's different from SCSI. But probably from our perspective, this model is consistent across both PCIe and different fabrics transports. Now, that was the host for the most part. At least we were talking mostly about where the queues actually exist. But you'll need a target for where the data is stored. And for that, you need to have an NVM subsystem. Now, the NVM subsystem is not just the NVMe storage, but it's made up of multiple components. For instance, the architectural elements that make up a NVM subsystem are the controllers, the namespaces, and the fabric ports. And then there are the implementation-dependent elements that have to do with the media itself. Now, if this were a storage presentation, we'd go into the specifics about what each of these different parts are. But for our purposes here, the most important aspect is that it's a consistent architectural model, independent of what fabric it attaches to. So what you see with the subsystem fabric ports, for example, is that they're associated with some type of physical fabric. For example, in the case of PCIe, it's a PCIe fabric port. In the case of, say, RDMA, it's associated with an RDMA NIC port. And so multiple controllers can be accessed via a single fabric port. Then the architecture defines that a controller is associated with, at most, one port. So the case where you have a host that wants to connect to a subsystem over multiple ports, what you'd see in that configuration is two controllers, each associated with one port. And then the fabric types are defined inside of NVMe over fabrics are PCIe, RDMA, TCP, and also fiber channel. And I know there's certain people in the panelists who are probably cringing already. But they can relax. It's okay. It's not required. Anyway.
Nothing. I'm saying nothing.
There's nothing. I know nothing. So I described the queues, and so what this slide is showing what is sent across those queues. And you're probably thinking, okay, wait, why aren't we talking about networking yet? We will, trust me. But these things will make a difference. You're just going to have to trust me for a moment. So what goes inside of the queues? All right. Well, when the host has an operation that it needs to be performed by the NVMe subsystem, it builds a command. Those commands are one of two types. They're either the admin command that goes into the admin queue. It's kind of a maintenance, not a performance path, or it's an I/O command that goes across one of the multiple I/O queues. So to keep it simple, in the I/O queues, there are only 3 mandatory I/O commands, which is a very small set of commands for I/O that are required for operation. For fabrics, we add 2 new commands. Basically how you establish a queue and how you operate it. In the case where the host is establishing a queue to the controller, we add a connect command, and that creates the association. And that connection obviously has a lot to do with what we're going to be talking about with the fabrics. We added another one called get properties, which is essentially a way to get at the controller state. And again, it's beyond the scope of this presentation, but NVMe has a lot of information about what the controller states can provide, and you can actually make network decisions based upon those controller states. There's a lot of flexibility in there. Sadly, we have to put that off to a different time. Now, it's good to note that these commands can complete out of order, so the host can submit lots of these commands. Depending upon the implementation of the controller and the type of the command, certain commands can be completed before other commands, so there's no ordering that's imposed upon a single queue. And this definitely makes it easier for the transport networks. It means you don't have to do anything special inside of the network to make things in order. The completion queue, as you may have guessed, is the way that the subsystem controller notifies the host that it's done. And so there's a command ID that's used to associate the completion with the command because they're out of order, and that's how you pair the two up. And then the SQ head pointer in the completion queue is an indication to the host as to what completion elements to consume. And then the host then uses that to free up the resources and allow it to submit more commands. Now, these entries are placed into the submission and completion queues and are processed by the host driver and the NVMe controller, respectively. Now, we've simplified things a bit to say that the host is pretty much the server and the controller is pretty much the storage target. But the reality is this can be anything. You can have a storage device which acts as both a host and a storage device. You can have a host that acts as both a host and a storage device. Where these things can be placed can be varied. It's not as rigid as it once was. So what you're seeing here is a generic approach to how this works. A submission queue entry is placed into the submission queue, obviously, where it gets processed by the NVMe controller. And then the NVMe controller then processes the command and sends or receives data if necessary, and then signals the completion of the job by placing a completion queue entry back into the completion queue. Sounds almost like a drinking game. So once that's done, the submission queue header pointer is updated, resources are freed up, and then the process begins again. And this is true for NVMe as well as for NVMe over Fabrics. Now, this may seem rather intuitive, all things being equal. However, there are two very important things to keep in mind. First, the time it takes between the insertion of the submission queue entry and the completion queue entry signaling the end of the road is the type of latency we're concerned with. Second, where these functions take place can change, and we want to make sure that we don't place these functions in a place where it adds delays and latency. Now, as we start to move forward and we start to see what kind of networks we're going to be inserting into this, it'll start to make an awful lot more sense. So this brings us, of course, to NVMe over Fabrics. So because when we start talking about the placement of these queues and the nature of the relationship between the host and the storage subsystem, we're going to be inserting that network somewhere in between, and somewhere in that area, right? In that model. And since we've got a tightly coupled relationship between those queues, it's going to make a big difference when we start messing around with those relationships. Now, as we record this presentation, there are now 5 official transport methods for NVMe over Fabrics. The latest one, TCP, was ratified by the board of directors in November. Now, the main goal of Fabrics is to maintain the same multi-queue model across the network. So you don't want to do something inside of the network that messes that up, because you want to provide a great deal of parallelism and low latency capabilities. Remember, NVMe is all about the latency. So one of the key features here is that you can independently scale the storage and compute to maximize the resource usage for specific workloads requirements. Now, we're going to be looking at many of these in turns, but it's good to have a broad overview to the different choices. But before I get started in that, Ethan, I wanted to ask, are there any questions about what we went over so far? Because it does get cumulative.
Nothing so far. No questions come in so far.
Right.
But I will say, Jay, I know you know this material cold. This is my 3rd or 4th time through this. I've actually been pulling stuff down from the SNIA and trying to read and keep up with it all, and I've talked to some other folks about it. It is a lot if you're not a storage person to keep it all in the head. But I think, you know, if we could compartmentalize the first part of what you were saying there, it's a lot about a lot of the bottlenecks that were in older storage methods. You know, SCSI, for example, are been removed. You can do a lot of parallelism now. You can ask a lot of questions, get a lot of answers at the same time, which is kind of changing the nature of what this looks like going over Fabric. Is that a fair way to compartmentalize the first part?
I think so. I think that if we have to distill it down to 2 things to remember, one is that we are not treating it as a device, we're treating it as memory, and as memory over networks. And 2, because of the fact that we have reduced the latency by orders of magnitude, all the lazy choices that we've made in networking are going to come back and bite us on the butt.
Okay.
And so the kind of things that, oh, we could skip because the latency of the storage device is going to save my ass, don't apply anymore. You really have to be careful about this. So think of this as memory at the other end of the wire, not a storage device. That's probably the key takeaway to remember out of this.
Got it.
Fair?
Yes. Yep.
Cool. Okay. So because of the fact that we're using the storage media within the memory semantics, it's no surprise then that remote directory memory access, or RDMA, is a key method for transporting NVMe. So generally speaking, there are two main versions of RDMA that are in common use, RoCE and iWARP. Now, each has its own networking characteristics and requirements, despite both being RDMA-based transports. For those of you who may already have some familiarity with HPC, RDMA is well understood in interprocessor communications. So this is really the first time we've actually been able to kind of popularize it for storage. It's been used internally in some of the back-end subsystems for storage, but from a host, this is actually still somewhat new. Now, the newest... Yes, sir?
For RoCE and iWARP storage transports, am I likely to see those in a converged scenario, or are those more likely to be found on a dedicated Ethernet storage network?
Well, we'll get to that in a second. It's an excellent question, but I have pretty pictures to go along with it.
Beautiful. Okay.
It's good because you're actually thinking ahead to. I'm leading you in the path to my my answers. Okay. So the newest official method, of course, is TCP, and we're going to give that a little bit of special attention later on as well. One of the things to look for, though, is that just because of the fact that all of these are Ethernet-based does not mean that they work the same way, nor does it mean that they have the same architectural considerations. And just keep that in the back of your mind as we move forward. Also standardized, but outside the scope of this presentation, are the Fiber Channel Standard and InfiniBand. InfiniBand works with the same RDMA rubric as RoCE and iWARP, but Fiber Channel required its own standard through the T11 Working Group of Insights. Now, I include this here for a reason that we're going to get to later on, particularly with TCP. So I have some links at the end of the presentation for more info about those, but for the remainder of the time that we'll have, I'm just going to be sticking to Ethernet, obviously. Okay. Now, things get really interesting when you start to look at what happens when you scale to multiple systems. You'll remember that we attach a Q pair to a CPU core and then connect it to an NVMe controller. One of the cool things about NVMe over Fabrics is that we can do this to multiple subsystems as well. Now, we didn't get any time to talk about the nature of SCSI versus NVMe, but this is one of the cool things that adds to the parallelism for NVMe that is difficult to do in SCSI. It's useful to know that an NVM subsystem does not have to mean an appliance or an array. It could mean a device that has multiple subsystems, or a logical set of constructs that are located in a distributed fashion across a network. Either way, we're going to be using each controller to provide its own separate set of queues instead of where we use a single set of queues for multiple controllers. Now, if you look at those green lines that connect to a CPU core to an individual I/O or submission queue, each one of those green lines can represent a network link in some fashion. So obviously anything that we do that's going to interfere with those networks or interfere with those relationships is going to be problematic. So we have to maintain that efficiency. Now from here, we really start to head down the rabbit hole. And we're going to be diving into some pretty specific and nuanced aspects of fabrics. In fact, this slide and the next 3 slides are arguably the most important ones in the whole presentation, because this is where we start to understand that not all transports are using NVMe in the same way. Once again, we're back to that fundamental point about NVMe. We're using storage in terms of memory semantics. So when we use PCIe, for instance, we're using a memory mapped model. Commands and responses as well as data use shared memory. Now we want to move outside of a server though. The propeller starts to spin the other way. We can extend that memory semantic remotely using remote direct memory access, or RDMA. The means by which data is transmitted can be done using capsules or shared memory, which we'll get to in a moment. Some transports, however, pass the data back and forth using messages or frames, and as a result, we need to be able to have the NVMe communicate with those types of transports natively as well. In this way, both Fiber Channel and TCP share similar characteristics about how they handle the command and the data transfer. More so than RoCE or iWARP, even though Ethernet may be the common underlying transport mechanism. And I know that we've got some people twitching at the moment. But this is where bindings come in, okay? And an NVMe over Fabrics connection is part of the specification when it uses the proper bindings between the NVMe layer and the transport layer. Now, the reason for this is that different transports have different requirements. A transport may require a separate transport connection for each admin or IOQ, or it could use the same connection for all admin and IOQs associated with a particular controller. In other words, these bindings are the glue that links all the NVMe bits to the transport bits. Now, this is how you can tell whether or not a solution is following the NVMe over Fabric specifications or not. I want to be clear, though, just because a solution may not be using the official specification doesn't mean that it won't work or that it's bad. I'm not saying that at all. What I am saying, though, is that simply having an NVMe solution that uses a network doesn't automatically make it NVMe over Fabrics in a standardized sense. Now, earlier we looked at a generic model for how the queues work between a host and an NVM subsystem. You may recall that I mentioned that this is where these functions took place could differ. So what you're seeing here is how NVMe over Fabrics works, which is slightly different than how it works for PCIe. You should note that for each of the different type of message transports, they exchange the same capsule format, but the mechanism that they use to send and receive it is transport dependent. The capsule is a collection of commands that I want to send to a queue, and therefore it only contains one submission queue element. If you have to send two commands, you'd have to send two different capsules. Once the NVMe controller receives the command, it needs to process it, and different types of transports have different methods of processing the command data further. So, for example, this is one example of how you can do one of those command data types transfers. Now, when you look at this graphic, we already have identified the submission queue entry going into the submission queue. Now it's time to do the command data transfer. Now once again, it helps to remember that we're talking about memory semantics, not device semantics. In the case of a direct memory access, such as PCIe and RDMA, the data is transferred using the transport specific method. For instance, what we're looking at is the actual data transfer mechanism, which happens once a command has already been received. Now, in PCIe and in RDMA, the way that this typically works when the command is sent across is that the command basically tells the controller to place data from a particular memory address into the host memory buffer address at the host. So when you want to do a read, for instance, what you're actually doing is telling the controller to write into a memory space. So this is a case where either a write or a read, when that command is sent across, indicates the buffer address inside the host buffer. In the case of an NVMe read, you're going to be placing memory back into that host buffer. That buffer address describes the operation, and the transporter is responsible for taking what's in the buffer address and using it to perform that data transfer operation. Obviously, this makes a lot of sense for a memory-based approach. In the case of RDMA, the submission queue is located on the target, and the submission queue entry gets sent in a capsule to the submission queue, where it gets processed as part of an RDMA operation, just like it's shown here. Now, if you're not familiar with how RDMA does this, don't worry. We're going to be covering RDMA in its own section. I like this. Are the wheels spinning too hard now?
You are wasting no words, Jay. So every sentence matters. It's that sort of a presentation, trying to keep up.
I'm sorry. I apologize. And here I was thinking, rudimentary for people. So this slide is an alternative. Remember we had the RDMA stuff, with iWARP and Rocky and InfiniBand. Well, this is the TCP and fiber channel way of doing things, and it's an alternative to the previous slide. But basically the same thing is true for in-capsule data. So in-capsule data is used for two purposes. The first is that if your transport doesn't have the facility to do the data transfer that I showed on the previous slide, then all data is essentially in-capsule. So the command plus the data comes in for a write operation, and for going back, it would be the completion plus the data. And that would be an example of a capsule-only type transport. The other scenario would be that if I had a device that is really low latency, and I would send the command, and I don't want to incur the overhead of having to fetch the data after the command's been sent. So in this method, there's an ability to put the data co-located with the command so that when the command is received, the data is right there with it. So this avoids a round trip need. And the way it's used is that the controller is told about this. The scatter gather list says, what type of address do I have in the case of a capsule offset address instead of a host address? So the SGL will describe what the address form of that data is. Ultimately, whether we're talking about in-capsule data or with controller initiated message plus memory methods like RDMA, we're highly dependent upon what happens within that gray arrow. So that right after all, that gray arrow right there on the graphic is where the transports, fabrics, or networks play their greatest role. So the reason why I showed these two ways of doing things, and I'm going to go back real quick just to show the difference here. When you look at this from a perspective of a gray arrow, that's where the proper networking methods have to be done. And you notice that there's a different way of handling the network in this approach than there is in this approach, yet they're both considered NVMe over fabrics, and they both use Ethernet. Okay, now that I probably scared the living daylights out of people. That's the fundamentals of NVMe over fabrics and what they're expecting. So it's good to reprise a couple of important points. First, NVMe looks at storage as memory, and I told you I'd be repeating myself on this one. And so it helps for you to think that you're networking memory systems and not storage devices. And secondly, NVMe is highly dependent upon low latency solutions, and as you probably heard, it does not react well to inconsistent or highly latent systems. So, having said that, and my apologies to the Hunt for Red October, we know that there are a couple different ways that message-based transports work. So let's take a closer look at the RDMA-based approach and understand how that works a little bit better. Well, for once, we have a term that is precisely what it sounds like. RDMA is the ability to directly access memory that exists in a remote location, but it eliminates the need to make multiple copies along the way. Now, specifically, it allows an application, which includes storage, to make data transfers from one memory space to another without the need to go through the kernel. Now, the hardware required to do this is something called an RNIC, or RDMA Capable Ethernet NIC, which is where the magic actually happens. Now, the RNIC manages the connections, the reliability, and the establishment of the dedicated queue pairs for RDMA. Now, in RDMA, they're called send queues and receive queues. It just so happens that these send queues and receive queues line up real nicely with the submission and completion queues from NVMe. It's queues all the time, everywhere, more queues. So one of the reasons why NVMe and RDMA work so well together is because those queue pairs line up. And because of this, you can daisy chain the queues together. For instance, the NVMe host driver would encapsulate a submission queue entry, including data, into a fabric neutral command capsule and passes it to the RDMA transport, which is then placed inside of an RDMA send queue, which then becomes an RDMA send payload. And then the RNIC at the other end receives the capsule in its receive queue, and then places the capsule entry back into the target's memory. Then when the command is completed, the process is simply reversed. So for all of you networking friends out there, this is the part that you're likely been chomping at the bit for. So let's talk about networking for RDMA. Oh no, priority flow control. Well, you've heard me talk about Rocky, and you asked a question about converged Ethernet. So obviously, Rocky stands for RDMA over converged Ethernet. And just how do we converge Ethernet? Well, we have to be able to run lossless and lossy traffic on the same links. So enter our old friend priority flow control, or PFC. So priority flow control is part of the data center bridging family of IEEE standards, and it enables you to run different traffic types over the same shared link, even if they have different requirements or characteristics. So in particular, we can isolate up to 8 different lanes or priorities of traffic. And we can modify the flow control such that one or more of them can become lossless. At the same time, normal traffic can operate as usual over a lossless or a lossy priority lane, and they can be all treated independently. Now, we're going to be talking an awful lot about explicit congestion notification moving forward, and I had a hard time figuring out where to put it, but considering we talk about it so much, it's a good idea to bring up the subject here.
Yeah.
I'll be returning back to this later on. So most of you may already know this, but ECN is a proactive method for notifying the endpoints, and it uses an IP header. So when we talk about IP-based storage, we use ECN, and that includes Rocky v2, iWARP, TCP, and basically anything that sits up above the IP layer. So ECN is used to first notify every device in a transit path that's capable, including the sender and the receiver. So when we get congestion somewhere on the path, we're going to set the bits in the IP header to notify congestion. We're still going to let the packets through, so we don't drop them like we would in a normal TCP kind of environment. We just inject the proper bits in the diffserv field values. And this is then taken by the receiver, which is then going to echo it back to the sender and then tell them to slow down. Now, we do this as long as someone in the path is setting the ECN bits to 2 1s. We echo it back and say, hey, hello, there's congestion, slow down. So when we do that, that way we want to notify the congestion before we start to drop packets, and then we have to wait for any kind of timeouts. Remember, this is storage, and it really does care about those timeouts a lot.
Yeah, now, and again, ECN is all about, you're not going to let TCP slow down because traffic got dropped. You're getting out in front of that. You don't want traffic to be dropped. So that's where ECN comes in.
That's right. That's right. Now you can do some interesting mixing and matching, which we're going to get to in a second. But it's important to note those two concepts are wind up being critical for various size deployments. So again, back into the memory world, RDMA comes from the world of InfiniBand. And there are a couple of different approaches to how to do this over Ethernet. The first is Rocky V1, as it's been known as now. It's been begun to fall out of favor, with most vendors preferring to work with Rocky V2. For NVMe in particular, I don't remember seeing any Rocky V1 solutions outside of testbeds. So everybody is working with Rocky V2. The earlier Rocky standard required lossless Ethernet across the board and could not cross an L3 boundary. Now, Rocky V2 builds upon the earlier specification and adds a UDP header, not a TCP header. iWARP, on the other hand, is layered on top of TCP and uses offloaded TCP flow control and management. Now, both protocols support the InfiniBand Verbs API, which is the application programming interface into the RDMA application at the upper layer protocols. So that's how an application that does RDMA can talk directly into the RNIC, specifically using those APIs.
Now, what's the difference between TCP, Jay, I think, which is kind of important. You're talking about offloading it to like a TOE NIC?
Well, with you could do that. It's not a requirement. Now, with RDMA, however, we're talking about two different things. You've got the RDMA aspect that needs to be processed, and then you have TCP that needs to be processed. So an RNIC would process the RDMA on the NIC, but you could have an additional TCP offload engine on that NIC as well, but it's not required.
Okay.
Those are two different things, and it's a very good question. Because I'm not even going to bother talking about Rocky V1 right now, because nobody's going to be using it for storage. Now, Rocky V2, the difference is primarily the IP header, and therefore it gets the nickname Routable Rocky. Now, that means that you can cross routing boundaries, but it doesn't mean that you necessarily should do it via multipath across a city. We're still talking about moving memory from one place to another, and we're still talking about extreme low latency. Now, iWARP is probably one of the ones that's the most opaque to a lot of people. And the obvious question about what iWARP stands for is something of a curiosity. Realistically, there's no official description for what it means. I don't personally care what you call it. It's just, people just call it iWARP, and it doesn't really matter what it stands for. Now, with respect to how it works, though, as we saw in an earlier graphic, the iWARP protocol replaces the IB transport protocol, which in turn sits on top of TCP. Now, alternatively, iWARP can also run over something called Stream Control Transmission Protocol, or SCTP, which provides some of the features of both UDP and TCP. Now, SCTP falls outside the scope of this presentation, except to say that it's message-oriented like UDP, but it also ensures reliable in-sequence transport of messages with congestion control like TCP. The key thing to keep in mind here is that while Rocky uses the IB transport protocol, iWARP uses its own protocol and can require additional elements for message boundaries and data reads and writes. Okay, we're not going to have time to go into the specifics about what each one needs, unfortunately. But it is important to note that iWARP and Rocky are not compatible. Now, you probably saw briefly that when we talked about the stacks, that they have different transport layers. Now, of course, with every rule, there's exceptions, but generally speaking, despite the fact that iWARP and Rocky are could be software compatible, just because of the fact that they're written to the RDMA verbs, there's still those L3, L4 differences that prevent the protocols from talking to each other. So the best thing to keep in mind is that if you use Rocky, everything should be Rocky. If you use Rocky V2, everything should be Rocky V2. If you use iWARP, everything should be iWARP. Okay, so this goes back to one of your earlier questions, Ethan. One of the advances in Rocky V2 has been the improvements of built-in packet retransmission logic. Now, even so, the specification does recommend that the underlying networks should be configured as lossless, that is, using PFC. It is true that having a lossless network is not 100% mandatory. However, for low latency networks such as RDMA and NVMeoF fabrics, it is better to deal with retransmission issues before they start, which means approaching congestion closer to the wire if possible. And we'll be showing what that actually looks like in about 2 seconds. Now, if you do decide to handle Rocky v2 with end-to-end lossless behavior, that is, you want to run the protocol using PFC-enabled links from host to target in large environments beyond 2 switches, you want to make sure that the L3 routers are configured to generate an L2 class of service priority for those Rocky v2 packets. Now, you'll need to look through the favorite vendor's QoS configuration guides for the appropriate setup for this. And this will be particularly important because you'll not just want, but you'll actually need to decouple the lossless traffic from other flows, particularly TCP. Now, when you combine this with proper QoS policies for the appropriate bandwidth sharing, you want to make sure that the devices can handle ECN. And okay, so the question is, what does that look like? Well, this is an example of a PFC only network, and if you've got a small network like a single switch or an in-rack communication, and you don't have endpoints that support ECN, you do want to implement PFC for such an environment. Now, remember, you'll have to treat these networks as deterministic. In other words, you want to treat these kinds of networks the exact same way that if you're planning a fiber channel or FCOE storage network, with well understood fan-in ratios and well understood oversubscription ratios. Because
okay, so
yes, sir.
The good question that's come in from Tom here in the audience, he actually wants to address that. If you, let's say we're going greenfield, we'll build something new. We got a new data center fabric we're putting in. Is there an oversubscription like rule of thumb that makes sense?
Yes.
That you can recommend?
No. because the reason is because it has to do with the application. So each application has its own oversubscription ratio requirements. That's why, for instance, you have some applications that say, we don't want you to use iSCSI, we only want you to use fiber channel, because they have well-defined oversubscription ratios. In fiber channel, for instance, in order to prevent PFC storms or head-of-line blocking, you want to have it down somewhere between 4-to-1 and 20-to-1 oversubscription ratios. Rarely do you ever see anything larger than that. In iSCSI or in NFS, it's not uncommon to do 50, 100, 200-to-1 oversubscription ratios because the applications aren't quite so time sensitive, aren't quite so latency sensitive. So generally speaking, most of these kinds of things, you want to find out what applications you're going to be using in these types of environments and what fan-in ratios they expect for deterministic storage. It's all application dependent. But typically, when you're talking about these kinds of systems, you're really looking at something a lot lower than 20-to-1 host to target ratios. So when people get into trouble or when they did get into trouble with lossless iSCSI or FCOE, they forgot that they were working with a deterministic storage network, and they got problems. They got a lot of PFC storms because they didn't handle that stuff right.
So related to this, when purchasing Ethernet switches, is there a chipset concern we have? I mean, you've been talking about Ethernet frames and IP packets essentially that gets bundled around all of these storage payloads, but is there like Mellanox has something that helps me with NVMe in their switching chipsets, or Broadcom or Tofino or whatever?
Well, I mean, from a standards perspective, no. I mean, anything that allows you to do 25, 40, 50, 100 gig switching is already got DCB enabled or capable, right? So being able to run PFC is a part and parcel of every switch's standard feature set. There's nothing internally that you need in order to be able to run NVMe over fabrics in an Ethernet situation. Most of the heavy lifting is done at the endpoints.
Yeah, the switch doesn't care that it happens to be an NVMe OF frame. He doesn't care. Yeah.
Nope, it's all about topology and architectural design rather than turning on a feature set, with the exception of making sure that you have the appropriate bandwidth set for your ETS setting inside of your switch. You want to make sure that you're not starving the network. That's the only thing that you really have to pay attention to, aside from whether or not you're using a lossless link or not.
Got it. Thanks, Jay.
Sure. No, this is where I thought we were going to get the most questions actually. And so if people
So
should have.
really what we're seeing here is that NVMe is a protocol that runs over the top, over TCP somewhere, or UDP, or does it run over IP?
Well, so remember the slide I had about the bindings?
Mm.
So the official NVMe over Fabrics transport has bindings to a particular transport type. And right
Yep.
now those transport types are RDMA,
Mm-hmm.
because it connects into the RDMA layer, not into the network layer.
Yes.
So you can run, so for example, if you wanted to run ICER, you could run it within the environment that has the RDMA connections into those bindings. It's not an official standardized way of doing it, but you could do it. You could also do it over TCP because there are bindings for how you can control the actual relationships between.
Yeah, so you can run RDMA over anything, because RDMA is basically saying I want to access this memory location in that server over there. Whether
Right.
you choose to run it over InfiniBand or Fiber Channel or Ethernet as a transport layer is kind of irrelevant. The challenge, I mean, I actually work with a customer who does run ECN on their network, but they don't, and it's all enabled. But the thing that makes it work isn't actually is just the fact that it's a non-blocking Ethernet architecture.
Right.
And so it's all, if there's no point in the network where congestion can occur. So they don't actually get a lot of congestion notifications actually happening. And they transfer petabytes of storage data over it and don't have any problems with it. And it didn't require, what I'm trying to say, I think, is, let me cut to the chase, is this is really easy to turn on. You just go into the switch and turn on explicit congestion notification. And if you want to, you can create a PFC, which is a cost setup for that traffic to flow down, but that's not necessarily needed. You don't have to have it in a non-blocking network.
Well, it's we're going to get to that in a second, actually. Whether you need it or not is there's a couple dependencies there that have to be addressed. If you happen to have a completely non-blocking, non-oversubscribed network, in theory, that you're never going to reach a point where you're going to have that congestion because there's just no bottlenecks in the network. And to that end, everything is pretty much just a fail-safe at that point. My experience, however, is that most Ethernet networks, particularly those that have been around for a while, are not so well designed. And so I'm kind of focusing here on what happens with the storage traffic specifically, as opposed to the overall general network design. And I hope that winds up being clear here. But when you need to take into account what goes wrong, there are some ways that you can mitigate this, and that's where PFC and ECN can actually come and be very handy.
And the other way to solve this problem from a implementation perspective that strikes me is just build your storage traffic on a separate set of switches. So go back to fiber channel model where there's a storage network that has this implemented, and then you don't have to juggle PFC and ECN versus all the data. So you don't have to juggle the storage traffic with the data network, and that can simplify things. So if you're struggling, it may actually just be cheaper to go back to the old way of doing the older way.
It may be, and in fact, if you have a very large storage network, given the fact that we could blow out a 100 gig link with 3 drives, it may very well be not only cost efficient but also management efficient as well. But you still want to maintain some really good networking practices for that storage network particularly.
Now, Jay, we happen to be coming up on time, but we can run a bit long. I just want to let people know I acknowledge this is supposed to be the end of our time, but I think Jay's got some more material to go through.
I do.
Jay, how much more you got, Jay, just so people know?
Well, when I did the test run, I actually came in well under time, but apparently
You've been asking questions. Yeah.
Yeah, well, that too. Let's ask you, all right? Because I have a TCP session and I have a networking for TCP that is worth knowing. Do you want to go into the specifics about the TCP protocol, or would you like to go into the networking aspects of what TCPs can do? You tell me.
Let's focus on the networking aspects as opposed to the under the hood mechanics. I think at this point, get the ultimate impact more, and let's see if we can wrap it in maybe 10 minutes.
I think so.
Let's do it.
So let's maybe just finish this really quickly because this will actually lead into the TCP session. It will actually segue quite nicely. So in this case, what we've got is an example where we have hosts that don't have ECN capabilities. And so we're going to use PFC support, particularly in the last mile. So we're going to be moving to ECN and use PFC as a failsafe here. And that way you can mix and match the hosts that are only PFC capable and hosts that are PFC and ECN capable. Now, realistically, what you could also do is have PFC to the host and ECN only in the core. Now, the reason why you do this is it's important to remember that PFC injects congestion into the network. It stops the traffic, which means that if the actual congestion is notified by the host, the actual core switches itself will mark the packets with ECN and then tell the senders and receivers to slow down independently. And that way you don't have to put PFC back beyond the first switch. And it's only down to the host or the actual targets. And so the PFC will inject the congestion, which is then picked up by the ECN, and they can work in tandem. Okay, so back into the NVMe over TCP. Let me focus on this a bit. Here we go. All right, so let's talk about building a better TCP, because now you can put the TCP networks, you can put TCP onto the, there we go. Hey, come back here. Don't know what happened. Now you can put the NVMe over fabrics onto TCP. So we want to make a better TCP, but in order to understand this, we want to note that one of the things that people have been talking about an awful lot for storage networks is throwing buffers at the problem. And when it comes to building storage networks, you really shouldn't be designing a network that has a lot of buffering, because buffering in a storage network is an undesirable condition. You got to treat it with great care. Now, when I talked about the lossless networks and deterministic storage, I mentioned them within the context of fiber channel and PFC-based networks, but it's really not a matter of the protocol, but the application requirements. In other words, you got to remember what the application needs and focus on that, because if you mismatch the application needs with the incorrect networking configuration, you're going to have a really bad day. So not all TCP stacks are created equal, and most common stacks rely on drops. And it's true that those kinds of TCP stacks require proper network buffering to handle excessive dropping. Now, newer stacks that look at round trip times and other feedback loops are optimizing for smaller or even quote unquote zero buffer networks. And this underscores the need for the accurate round trip time estimators. So it helps to know which stacks that you're using. And I want to try to keep marrying this back to the NVMe needs, because remember, we're talking about moving memory across the network. Now, TCP flows have a tendency to grab as much bandwidth as possible. And NVMe over TCP adds the additional greediness of never blocking on I/O, unlike some other TCP implementations. For instance, every send into the wire is with the message, "Don't wait." And we rely on the connection to pick up wherever we leave off when congestion hits. So this allows us to multiplex between connections on the same thread, and we never block and never schedule those TCP connections to sleep. All NVMe over TCP flows are long-lived flows, and they're low latency flows. So this is kind of the worst of both worlds from a TCP perspective. The reason is because it has a very aggressive impact on the network. And as a network, obviously TCP will react to that aggression by dropping and retransmitting. And so that's how TCP, actually has to handle its own congestion control, because it needs that retransmission. So the buffer question becomes something of a Goldilocks situation. On the one hand, if you don't have enough buffer, you're going to have poor utilization. And if you have too much buffer, you're going to increase the latency. So as we know, NVMe over fabrics is latency sensitive. So simply throwing more buffer at the problem is going to have adverse side effects on that performance. So the trick is to have just enough buffers to get the possible link utilization and latency. So as we've already probably, kind of revealed our hand here, there's two different methods of solving this problem. The first is to increase the buffer size in the switches. And the second is to be more proactive and tell the sender to slow down before TCP packets get dropped. And the reason for this is because of what happens with TCP Incast. Now, most of you probably are well familiar with what happens with TCP Incast, but from a storage perspective, this is something that is actually going to probably be far more prevalent with NVMe, because in NVMe over TCP, every queue pair is its own TCP session. So if you've got multiple queue pairs from multiple hosts with multiple CPU cores, they each have their own TCP session to a particular target. So TCP Incast happens when you have synchronized sessions that arrive at a common congestion point at the same time, such as when you have an NVMe over TCP flow with multiple IO queues coming in at the same time, with each with their own TCP session. Now, in this case, each of the TCP sessions are going to grow the window until it detects congestion, and then it's going to trigger the packet loss. And at that point in time, all of the TCP sessions, they're going to back off at the same time. Now, that is where everything's going to stop, and you get, incredible latency, and bad things happen. And of course, NVMe over TCP starts to panic. So one of the things about the Incast, and that's what we call the Incast collapse, is that you get these long-lived flows, these elephant flows like NVMe over TCP, and they fill up the buffers. And historically, those kinds of buffers handle every flow the same. But obviously, that's not the best solution, particularly for NVMe over TCP or NVMe over fabrics, which are both long-lived and latency sensitive. So because of the fact that we assign TCP sessions to individual queues, the likelihood of a multi-queue environment invoking these kinds of data flows to the same destination is going to become far more of a reality than we've experienced in the past. Now, obviously, we could add more buffers to the problem so that you avoid the overflow problem by adding in additional latency, but at least you don't have the overflow problem. But the other approach is the ECN approach, which is to be more proactive before the actual drops happen. And that's where data center TCP comes in, which uses explicit congestion notification to instruct the sender to do this. So explicit congestion notification is the notification markings for congestion, but DC-TCP is the algorithm to achieve that high burst tolerance and low latency with the shallow buffers. So instead of using a blunt force instrument where the presence of congestion can cause a severe back-off event, we now react in proportion to the extent of the congestion. And that way we can actually have lower buffers, shallow buffers, and still have better or even, at least the same throughput that TCP without having all of that buffer space. So realistically, what happens is we get consistency across the board. So supposing we have a sender that is connected to a host with multiple queue pairs, each with their own TCP session, notification is going to get back to the sender on a per queue basis. And that way the sender can understand what's happening and pull back on the traffic, because not all submission queues and completion queues will be handling the traffic at the same time in the same manner. So now we're in the home stretch, and I realize that I think I got the timing hopefully better. But let's return to this graphic, which seems so long ago now. We've spent a little bit of time with the network, but we can't lose sight of the nature of the relationship between the host and the storage. So while that simple gray arrow will represent the connection between the host memory space and the NVMe controller memory space, we've seen that there are a lot of players to be named later that can help, that can affect how this all works. So we want this arrow to be as short as possible and with as little variability as possible. But in reality, we've got multiple switches, and there's multiple gray arrows, and there's multiple buffers, and every single one of those gets put into that gray arrow between the host and the target. And that's why NVMe over Fabrics has some very specific storage requirements for the switches. And the impacts can be enormous, given how much throughput we're talking about. And obviously, if you plan this incorrectly, you could get a lot of headaches. So last but not least, this is a quick summary. When you start to think about using a particular storage networking protocol for NVMe over Fabrics, it helps to remember what the expectations are from the NVMe side, whether we're doing a memory transfer or whether we're doing a capsule transfer, and what the actual expectations of that Fabrics binding is going to wind up being. Ethernet's not monolithic. And so unlike SCSI, which is sort of, being able to throw the packets over the wall, there's a tightly coupled relationship between the host and the target with that network in between. So understanding how storage reacts to the network and vice versa is going to be the difference between a really good networking solution and a nightmare one. So this is the last slide. It's got a whole bunch of information that you can check on. I suggest taking a screenshot for it. But I do want to thank Packet Pushers for inviting me to come and talk with you today. I apologize for going long.
Thanks, Jay. This was great. A ton of information. As I mentioned, I've been through some other slide decks that you've done on this and trying to get all of this into my head. And I saw some of those slides and graphics appear again in this presentation. And it's a lot. It just takes a lot of going through it to understand how it all goes. But thank you for applying this directly to networks and giving us a clue of what we're in for as NVMe begins to, I don't know if take over the data center is quite right, but it looks like adoption is going to be serious and we're going to see a big uptick in it. So
yeah, I agree. And we're already seeing a lot of questions about it. So people are asking the right questions, which is good. Yeah. And I think that the fact that there are so many things in here that are nuanced kind of underscores the fact that we have been able to get by without knowing a lot of the inner workings of details about how storage networks really work, as long as we could, create a network that was passable. And I think at this point in time, we kind of have to start to realize that, there are dependencies here. It's not just about putting a packet from one device to another. There's more to it than that. And at least people are asking the right questions about it.